Okay, so welcome to another edition of Voxel Fridays on and on Friday. Um, so the plan here today is I did some off-stream work, and I said I didn't want to do any work off-stream, so we'll review everything I did off-stream. Yeah, if anybody knows, like, what is there some way when I restart the stream to like make sure people get refreshed? Is there something I can do at my end? Because I always restart the stream to make it so that the YouTube archive starts at the right place. Um, so yeah, so the plan is to review what I've changed. The last time I was dealing with really weird performance results, and I decided to follow up on that offline so that I didn't have to worry about OBS interference. And I got some useful results. Yeah, I guess what I can do is just say out loud, restarting the stream, refresh if necessary, right before I do it. Maybe something like that. So I got a better understanding of what's going on timing wise. I verified that the find LSB stuff that we were looking at was a compiler bug or some limitation of the old hardware. And we'll talk through all that. And since we're reviewing, I think what I'm going to do is I'm going to give a detailed description on the whiteboard of what's going on in this crazy code, because I haven't really probably explained it very well. So we'll see if we can do a better job of explaining what's going on. Does that make sense to everybody? Okay, so go back to main. So here was the one we were doing. So it's the correct data, but the wrong textures, but the correct voxel shape. Why is this creaking? Hang on a second. My mic is creaking. Okay, hopefully that's fixed it. And I've added debug data that is incorrect, I think. Oh no, the quads is correct. The debug 999 is because there's nothing being debugged. So in this particular thing, it's adding all the faces. So if I stick my head in the wall, there's these internal faces. So it's about 3 times as many quads as it should be. If we go back to the original slow one, you can see 368,000 quads, or quad pairs, basically, face pairs. And the debug number is actually the number of voxels that are visible. So you can see most voxels only have one visible face, which is, because it's a wall. So so the inside and outside are the only face pair that's visible. So the number of face pairs is just barely more than the number of voxels, which is correct. It's what we expect. So the new one is 3 stages long. That's this code here. Everything gets pushed out to memory after the first stage, and then gets read from memory in the second stage, etc. And if we go back to that, this one. what is the speed of this one currently? It's all kind of hacky because the meshing, yeah, 0.59. We were talking about this. We were hitting sort of a 0.5 milliseconds, and that seems like a lot when we're not really doing a full map, and like that's going to be a performance issue potentially. So in the new one, it'll eventually be 4 stages. It's 3 stages right now. This is the slow version. They're using Find LSB. So let's switch that, and we'll go through all of this in a minute. VRAM. It's this one. Yeah, this. Okay. So here you can see the total time now. It's 0.09, 0.06, and 0.07. So it's faster. So let's talk about what's changed, and then we'll go to the whiteboard. So this is the old one. And so the idea in this old one was we make this occupancy bit array 10 by 10 by the height of the thing. And we put that into shared memory. And the thing I was starting to notice when I was playing with this, so we put that into shared memory, it's these bit arrays, and then we go and read out the center one and the 4 around it. We'll explain this on the whiteboard in more detail. And we can compute with some bit math which ones actually need to be drawn. But we only do that here to like compute whether there is one at all, and then we go through and do it again to do this other thing that we were doing, and then we go through and do it again. And I was just assuming, oh, well, this is just in bit math and this shared memory is local to the core, so it should all be fast. But some of the stuff we were doing, I was starting to notice it seemed like maybe this was actually taking a noticeable amount of time. So maybe we shouldn't recompute it multiple times. The other thing is that you know, I had done some math to say that maybe this is okay, at least if we're at 512. And the thing is that we don't actually have to allocate the full array. Like, so originally I was thinking, well, we'll just make the total height of the scene half as big. But you don't actually have to allocate the whole height of the scene at once. You can just do the top half and the bottom half on 2 separate frames, or as 2 separate calls, or just with 2 separate shaders, or you could do it iteratively. There's a bunch of things you can do. And so especially if the 980 Ti maybe has less memory or something, I thought maybe it was important to bring this down. And so I did experiment with that in the new one. And we're currently at this. I haven't tested, I did some bug fixes that maybe has changed this, and maybe I could push it back up larger. That's something to investigate in the future. But this new one, we only iterate over this once. So this is, we iterate over the command list. This is all cut and pasted from the old code. Then we go through the bit arrays and we do it once. And then here we output a thing, and we'll talk about what this is doing. Okay, so in fact, we're going to switch to talking about what it's doing. Dun, 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 dun. Okay. Also, I'm a little sleepy again, but I'm not planning on actually coding much, so I don't think it'll be a problem. Okay. Basic premise is that we have a candidate voxel and this, we know that this voxel is solid. So then we look at the neighbors. So we have 6 neighbors, 4 in the plane, 1 above and 1 below. And if any of these are open, and if any of the 6 are open, then we assume that we should draw that face, and therefore we assume that that voxel is visible. So that's the basic test. And so we can do that in binary arithmetic by saying if this is a 1, the green one, the green is a 1, and then if any of these blues, A, B, let's label the top of each face, A, B, C, D, E, and F. If any of A, B, C, D, E, or F is 0, and the center is 1, then we want to draw it. Then we want to mesh it. We want to create a mesh, a corresponding mesh. Okay, I'm going to erase that. Just wanted to establish that. So I can write out what the math is for that. So that is F, sorry. So let's call the center X. Well, let's call it V because that's what V for value is a common thing I use. It's also visibility. So it's V is true, and either not A, or not B, or not C, etc. And we can apply De Morgan's law to that, and that becomes not A or and A and B and C, etc. Which you can think about logically. We're saying we don't need to draw this if all 6 are also solid. As soon as one of the 6 isn't solid, we draw it. So if all 6 are solid, we don't draw it. So the don't draw condition is all of them are true, then negate that. So that becomes, if we use bitwise arithmetic, that becomes tilde A and B and C and D. Is the microphone blocking it? No. So that's the way we can use bits to determine whether a voxel should be meshed. So we have a big chunk that's 256 by 256, and we dice it into little chunks. And we end up with a little chunk that is 8 by 8. So, sorry. We have a big, we're rendering a chunk. We're meshing a chunk that is 256, 256, 1024. We dice that into chunks that are 8 by 8 by 1024. If we look at that chunk from above, so these are each big tall columns coming out. Then when we're processing that chunk, we need their neighbors, which are these. We don't need these corners, but we allocate them, and that leaves us a 10 by 10 grid in the code. So in the old version of this, go back to the code for a moment. So in the old version of this, that's this occupancy bit array 10 by 10 by Z words. So we have a 1024, but a word stores 32 bits. So we have 32 Boolean flags bits. So we divide this by 32. It's the same thing. And we allocate this 10 by 10. So that's what the old code did. So if we think about that in terms of this illustration, if we turn this illustration now on its side, we'll only do 4 instead of 8 or 10. Conceptually, we have 1024. Ten by 10 by 1024 bits that are stored in the code as words. And these are grouped in groups of 32, which I'm drawing here as 7. And what that lets us do is grab a 32-bit word from, say, these 5 squares, which then produces right, that same configuration we saw before. but you need an extra. You'll need one extra entry here and one extra entry here. And so you have 32 spots here, and you have all their neighbors because you have the 4 neighbors in that plane that way, and within that single column and those 2 ends, you have the up and down neighbors, because again, this is rotated on its side. So you, instead of doing this math once per voxel slot, you do it once per 32-bit word. You do this math, and that gives you back a list of which voxels, or a bit array, 32-bit bit array of which voxels need to be meshed. So now, if you take that math and you flatten that out, that just becomes this one long 32 bits, 32 bits, 32 bits. And each of these has a 1-bit if it needs to get converted to a mesh. If the corresponding voxel needs to get meshed. And I'm going to erase all this now. But so if we take that formulation, let's look at the code. So here we grab the 4 neighbors, north, south, east, and west. Here we've split up we're computing north and south and north and south and east and west and down and up. That's what's being computed here. And then we invert it and AND with V, which is exactly what's on the blackboard. That's the formula that's on the blackboard, the whiteboard. And the way the top and bottom are handled are with this shifting through. You just shift the main column of bits. You shift them left and right to get the up and down, and you have to fill in the ends. So all that is how the old code was working too. So when we go to the new code, no, that was, oh, I loaded the wrong one. That is the new code. Okay. Okay, so yeah, so let's talk about the problem. So we do this nice, efficient calculation that computes 32 voxels in parallel, and we're doing that in each SIMD lane. And what that might compute in 4 SIMD lanes, one of them might be like a wall, and it's going to be 1, 1, 1, 1, 1, 1, 1, 1, etc. Another one might be wide open and empty. Maybe it has one voxel in it. Another one, is a mix, 00111. There's in the SIMD, there's 32 or 64. We're actually doing 64. Well, it's lockstep, so it's 32. There's 32 of these calculations. So in a single hyperthread, we've computed 32 lanes, and each lane stores 32 voxels. So we have 1,000 voxel slots, some of which are zeros, some of which are ones. So some need to get meshed and some don't. So what we want to do is turn those into meshes. And a way to do it is you can iterate through from 0 to 31, say, is that bit set or not? If it is set, okay, it's a visible voxel, let's mesh it. But if you do that, some SIMD lanes will have to do that processing, and some SIMD lanes will only do a little bit of processing, or partial processing. And that's not very efficient if doing the meshing takes a lot of work, because you have a low utilization. You have a lot of idle SIMD lanes, CUDA threads. So what we'd like to do is find some way to de-sparsify this, to turn this back to dense data so that all of the lanes can be doing useful work. And that's what I've been struggling with this whole time, was that process. And I have a version of that working now that uses the find LSB thing, so it doesn't work efficiently on this hardware. But I ran it on a 4090 and it runs fine. It doesn't have the weird slowdown. It's also not that much faster than doing it the slow way, but we also need to somehow figure out which textures go on which faces, which comes from the command list. We couldn't store that as we're going because it requires 32 bits for every voxel. And we were trying to pack every voxel down to 1 bit. We had to also store 32 bits, wouldn't be efficient. So we're going to do that in a separate pass. So we want to do that computation only on the voxels that need it. So again, we want to densify. That's a reason to densify. So what we do, it's over here. There's also many lanes that are just all zeros. You're out away from the buildings in open space or whatever. So there are lots of SIMD lanes that just don't need any work to be done. So what we do, too bad I erased it, so we've computed this 8 by 8 by 1024 grid of bits for where the voxels are that we want to desparsify. And when you break them down by 32-bit words, lots of the words are 0. Don't have any processing needed. So what we're going to do as a first step is we're going to go through all of the 32-bit words and if the word is non-zero, we're going to write to memory what it is and where it is. So we're going to switch from just storing all of them to storing the location, not the location in memory, but the location in the grid, the X, Y, and Z. This is X, Y, and Z. Z is vertical in my world. And this is on its side while we're looking at it, because that's the way the 32-bit numbers kind of go. So we'll go through and we'll save away the X, the Y, the Z, and the bit pattern. take all of this and we'll write that out to a new piece of data. In that new piece of data, this value is still sparse. So all we're doing is striking out the zeros. So we still have to deal with this data being sparse. So what we want to do, let's go back to the code for a second. So here's an example of what the logic for this looks like for how to process one of these things. So we packed in, it's stored in a vec4. We'll talk about why. So it stores in X, Y, W is the word. So it's the index through the bit array of where that word was. And then instead of storing V, it actually stores 3 numbers, which I'll explain in a second. Or instead of storing viz. But anyway, so the naive thing you can do is you just loop through all the bits. And if the bit is non-zero, then we create what we call a voxel job, which is just the X and Y and Z coordinates and which faces are visible. And we output that to a new area of memory. So we take this data, we find all the non-zero entries, and we write out this 16-byte thing that contains that data to memory. Then we start a new compute shader that reads these and writes out this stores Z over 32 effectively. So we write a new compute shader that reads these entries and outputs where the bit is 1, outputs X, Y, Z, and what we call flags. This is the face. It's a list of which faces to draw. So the compute shader sequence works as follows in the current code. It first does this operation. Well, first it builds the big grid of occupancy. Then it goes through and computes this operation to produce this data structure. That's all in the first compute shader. Then the second compute and then outputs this data. Sorry, that's all in the first compute shader because this lives in shared memory. Then the second compute shader takes this data with the 32-bit words with the zeros eliminated and builds this data, which voxels actually need to get processed because they need to get textured, which we're not doing yet. The fourth shader then runs through all this data and produces the mesh data corresponding to it. And the missing third step will help with doing the texture, choosing which textures go on which faces. The interesting thing about this step, right, we were trying to get to this in the code. So in the code, we do this. And the thing about this is that we actually are running 32 SIMD lanes in parallel, and only some of them does this happen. But it does, the way GPUs work, it's doing all of this processing for all of them, just not actually just suppressing it. But those lanes are effectively idle. The utilization is low. This is the desparsification problem. So, and this is happening in the second one, after the first one wrote out all the non-zeros. So a trick you can do is the find LSB thing, where, you know, suppose all the lanes had 5 1-bits, but they were in different spots in all of them. Then in this code, every one of the 32 times it would have to, one of the lanes would trigger into this code, and it would take the time it takes to run this loop 32 times. But if every lane has at most 5 bits set, then this code finds the set bits, processes just the set bit, and loops, and this loop will only run 5 times. So it's potentially a lot faster, except for the bug that causes it to be slow on the 980. But for this to be efficient, we want that only 5 bit set kind of constraint. We want all the lanes to have a similar number of set bits. And I did talk about this on Monday, but I wanted to be a little more explicit about it. So how do we get these to be more coherent, to have a similar number of set bits? That is part of why we produce this data structure. We write out all of the non-zero 32-bit words to memory. And what we do is we actually, instead of writing out one list with all of them, we write out 8 lists. The first list has only ones that have exactly 1 bit set. The second has exactly 2 bit set. The third has exactly 3 bit set. The fourth has exactly 4 bit set. The fifth has 5 to 8 bit set. The sixth has 9 to 16 bit set. The seventh has 17 to 24 bit set, and the eighth has 25 to 32 bits set. Then when we process in the code, we actually go through the 8 lists and that way when we pull the data out, their counts will always be similar. The number of set bits will always be similar, and this path will still not be efficient, but this path, the find LSB path, will be efficient. However, it turns out this isn't actually doing that much work, and so running it 32 times isn't that bad. It seems like it's dominated by the cost of writing it to memory. On the 4090, this path took 2 milliseconds, 0.02 milliseconds, and this path took 0.03 milliseconds. That's, you know, down in the sig figs. Maybe they're the same. Maybe this one's actually faster. I did have a different test case where this one was faster on the 4090. But I didn't spend too much time on it because the 980, you know, is broken for that. Let me see if I can share. If I run it, the 4090, it's on my OBS machine, streaming machine. Do I not? Oh, I do. Right, I see. OBS. If I add a source, window capture, create new. Yeah, so you can see match 0.02 and 0.03. And then this is the conversion to actual quads at the end. Up here somewhere, I think it says NVIDIA GeForce 4090. Yeah. So I think that covers what I wanted to do on the whiteboard. But so now the total time is 0.08 plus 0.08 plus 0.11, which is about 0.27, which I'm pretty sure is faster than what we used to be getting. Oh, except this is actually the wrong one. Oh, no, it's not the wrong one. It is the right one. It's, why is the quad count so high? Oh, maybe I haven't debugged this yet. Or maybe I just have some hacked code in. That's from Voxel. Yeah, I do. I think I haven't actually debugged that this works yet. Yeah, okay. Right, so there is one thing I haven't talked about yet. So these gaps. Those gaps shouldn't be there. That's because I left in something. That's going to be... I thought I turned this off. Yeah, I turned this off. There's like a +1 somewhere probably. Oh yeah, so I haven't really talked about this. Okay. So in the old system, as I said, there's a 10 by 10 by 1024 bit array in shared memory. And that's inefficient, and we can hack it down. So now remember, the way we're using it, I deleted that, is that, you know, there's a column in here, and we're looking at its neighbors. We're using these multiple columns in here to look at their neighbors. And remember, there's this trick for how do you know for a given voxel somewhere in here how you get what's above and below it. Remember, this whole thing is rotated. The z-axis is that way. So how do you get what's above it and below it? And that is just, well, it comes out of that same column. It's the next bit or the previous bit. And at the very bottom and at the very top, you don't have data, but that's okay. We can fake that. We know what it should be synthetically. But then I talked about how instead of always allocating the 1024, we can allocate a much smaller amount, say 256, and then we have to do 4 iterations. We repeat 4 times. And because it's compute shaders, rather than looping 4 times over the 4 elevations, starting at 0, starting at 256, starting at 512, starting at 768, instead of doing that, we just run 4 times as many compute shaders and do 1 on each slice. But when we do that, now we don't know at at the topmost and the bottommost, we don't know what the next voxel should be. We don't know what's above and below the given voxel. So right now, we err on the side of just displaying the voxel. We just assume that the top and bottom of those voxels are visible, and we always output them into the mesh. And I started to work on doing better, but I didn't get it working, and I'll come back to it. And it never is wrong to do that. It just produces faces that you can't see potentially, but it never produces incorrect data to do that. And where I actually ended up at in the current code is actually 64. With what I was testing, that was the fastest, but I had a bug at the time when I did that testing, so it might be faster to go back to a larger number. We can actually test that. So .11.08. Okay, that's in. It should be this one. Oh, here it is. Yeah. I think I have to make the color match. Yeah. What do I make it now? 256. .16.06. .11.06. So it's faster, the width is smaller. So in fact, we can push it all the way down to 32. That's 0.09, what was 64? We're probably in the noise area, yeah, 0.1 or 0.1. So it's probably fastest to actually just be 1. I have no idea how I would choose between the two things you're describing. They have no connection to how I think about programming jobs. I've never pursued money, so like that's just never been a factor for me. So this suggests, remember I said earlier that it seemed like maybe the shared data is not that efficient to access, that I had some evidence for that. So I reduced the size for the sake of occupancy, unrelated. This is voxel occupancy. I mean for the sake of GPU thread occupancy, hyperthread occupancy. I talked about this in the previous stream. The larger this is, the fewer hyperthreads you can run. And so I brought this down in pursuit of that and saw it getting faster. But now it's so small that this is just 1. So it's now just 1 uint, 10 by 10 uints. But I had also noticed that I had evidence that reading it is not necessarily that fast. So that suggests, now that we're down to only 1, that another strategy to do would be to not store it in shared memory. Now, the reason we store it in shared memory is because then we have 8x8 SIMD lanes running. They compute 96, so 64 SIMD lanes running. They compute 96 of these bit arrays. So they only have to do a little bit of work. They each compute two, effectively, and some of them are wasted. And then they can share them between each other. And so we only compute effectively 128 words, if this comes down to one word, which is at the moment. Then we're doing the work to compute 128 words. We only need 96. But we're doing the work to compute 128 words and then sharing them. But each one needs, so if we didn't share the data, each one needs 4 neighbors plus itself. So we'd need to compute 5 for each one. And that would be the equivalent of 5 times 64, 320. So we'd have to do 320 worth of computation and so we'd be doing even more redundant computation, but we would just not use the shared memory at all. We wouldn't have that as a resource that we're contending over, although now it's small enough that it's probably not an issue. And but we wouldn't have the slowdown of accessing it. So it's a trade-off of we recompute more, but we don't have this extra memory accessing. So that's another strategy we will try in the future, is just not using the shared data to store this at all. So I don't think I'm going to do any coding. I think that's it. I can review all of the code in detail, since I said I didn't really want to do it off stream. But this may not be the one that ships. We're going to still try more strategies probably. So I'm not sure it's worth, like the strategy I was just talking about. So I'm not sure it's worth going into detail on this code. But I can if people think it's important to do that. I think my personal plan right now is we won't, and we'll try other methods. And if this is the method that ends up being the one that ships, quote unquote, then I'll make sure to review it at that time. So yeah, I think that's it on talking about this code. So we're just going to turn it over to questions from the audience. And I'm going to try in the future to confine Voxel Fridays to Friday. But this one, I did it on Monday because I had skipped it the previous week. And then I did this one today because there were such weirdness on Monday that I really felt compelled to run it off stream, so I didn't have OBS messing it up and I could look at the timing and I could run it on the 4090. When we ran on the 4090 a second ago, those times are with this is running on the machine that's doing the streaming, so it's actually doing a 1080p compression and doing a 1440p compression, both simultaneous. Obviously all that uses custom hardware on the NVIDIA card that doesn't directly affect the GPU, but OBS and that could still be eating some amount of time, but obviously it's pretty fast. Maybe it would be faster, we don't know. But certainly on a 4090, building geometry in a millisecond is not going to be a problem. I mean, hopefully the idea is that on a 9080 Ti it's a millisecond, and on a 4090 it's a tenth of a millisecond or something. So that is what was done here. Okay, any questions about anything? Doesn't have to be about this code. You'll have to rogue z on main.c. Oh, yeah. Typed on the wrong keyboard. What do you think about Total Recall? Wait, is that the one that got remade? So do you mean the remake? It's fine. I'm a fan of Philip Dick, and Hollywood has always, I don't want to say ruined, but perturbed his stories pretty heavily. Total Recall is one that's so very extreme. Just takes a little kind of funny short story and turns it into this whole production. Like obviously it's got lots of great little bits. I'm not sure I'm really a fan of the ambiguity in the ending. Yeah, I would say that when facing a choice like that, you can try to do things like, make pros and cons, make columns with pros and cons and stuff. My A common strategy that I use is that if I feel like I really prefer one over the other, but that I don't have a rational explanation for why, then I just go with one I prefer. And if I can't immediately tell that, the trick that I used to do, I haven't done this in a long time, is you flip a coin and listen to your mental thoughts when you get the result. And you say heads, I do A, tails, I do B, and you flip the coin and it comes up heads. Do you say to yourself, I wish it was tails? Like, you feel an impulse like that. You lodge for that and you ignore the result of the coin flip and you just pay attention to what that voice is saying. Do I still play guitar? I don't know if that's coming through. No, it's not coming through. It's coming through in the mic. I love that you just immediately have it in hand without even having to move your chair. Yeah, it's actually because I'm recording samples of the guitar that I'm going to use for a project to have a fully sampled electric guitar. And it's really slow. It's really tedious. So I do a little bit of it and then I set it aside and do something that's not tedious. And then I come back to it. So I have to have it right there. So it's convenient so I can convince myself to do a little bit of it at a time. This is a Steinberger Spirit guitar, which is a guitar that has no headstock. It's kind of an old 80s thing, I think. I own a Fender, an American Fender Strat. I think it's an American Fender Strat. And then at some point I bought, well, so like I have an Ibanez knockoff Fender Strat, and it weighs a lot less. And I found that it was more comfortable to play it if it weighed less. So I kind of started hunting around for guitars that weighed less. There are ones that weigh even less than the Steinberger, but this felt like a good compromise of quality. So, right, it doesn't have a big thing here. This is relatively small, which cuts down on the weight, and it doesn't have the headstock, which cuts down a little bit of weight. So this is a relatively light guitar, and that just feels more comfortable to me. But I have right over here, it was right here, and I moved it because I didn't want it on stream. I also have this guitar here, which I just bought. It's an 8-string guitar. Which is the guitar I've been composing on lately. Normally the 8-string guitar is just tuned with 2 low strings, but this is actually tuned weird in a way that I don't really want to talk about publicly right now. I have a couple old synthesizers, and then when I quit Epic, I bought a couple real analog synthesizers. There's a new, relatively cheap, like 8-voice analog synths that have come out in the last 10 or 20 years. How do you tune the Spirit? So actually I have this Spirit here, and I have this Spirit here. This one, the other one is also tuned weird from before I bought the 8-string. So the Steinberger Spirit, it's because it's black, it's hard to see. So it's got 6 little knobs right here that you turn to tune it. And then it's a floating tremolo that I never use. And it's another big knob here that tunes right there, that tunes that tunes all of the 6 strings at once. Yeah, I have a modular synth set up, but of course that's only 1 voice at a time, and that's why I bought I bought a couple analog synths that have 8 voices. There's like it's a Prophet 12, what's the big Prophet? I don't remember, but it's a 6/12 voice Prophet 5, right? Prophet 5 or Prophet 6, whichever one it is. A knockoff of those, like a Behringer or somebody makes one. Like Behringer is just amazing in terms of making cheap music equipment. Um, that I guess they're kind of controversial or something. But can you lock the tuning knobs? Must be annoying when playing if your thimble goes out of tune. They're really hard to turn, those knobs, and they're down out of the way. So I don't think they tend to get turned accidentally. It is intentionally part of a locked, quote unquote, locking tremolo design that's not really locked. But that's why there's that tuning knob I mentioned that tunes all the strings at once, because the idea is that you tune it, then put in the tremolo arm, and the balance may change a little bit, and you can bring it back into tune with just turning one knob at that point. But I've never used it because I don't use the tremolo arm. So yeah, so I have a couple analog synths. I have a separate music room. In that music room, I have a couple analog synths. I have an old Juno Roland synth. I have around 10 guitars, a couple basses, a mandolin, a violin that I've never learned, an electronic drum kit that's not set up, and then I have a giant set of pedals that I documented on Blue Sky. Extreme pedal board, I call it. No, it's not a Floyd Rose. It's a special Steinberger Spirit. It's called R Trem, I think, this one. There's two. There's a later Spirit that's a fancier tremolo, and I believe this one is called R Trem. The letter R Trem. So yeah, the Extreme pedal board is sort of the most interesting thing of all that. Extreme pedal board is just a collection of guitar effects pedals arranged for studio use. So traditional use of a pedal board is you have a bunch of effects pedals on the pedal board on the ground, and you're a performer performing in front of an audience, and you need to be able to switch them quickly so you can click on the pedals, but all the pedals have little knobs on them that you can use to adjust their settings as well. So in the studio setup, you want access to the knobs with your hands, and I don't want to keep bending over, and I don't want to keep going, oh, well, on this song, I'm going to use this effect, so let me grab it from my storage, and let me plug it in, and let me tune the knobs. So I have this whole setup with about 100 pedals that are just all set up and all wired together, and all accessible by hand, and you can see it on Blue Sky. I can link it. I'll find it. Here it is. It turns out they don't draw very much power at all. Like, I have them all plugged in through one wall connector, and I used to have a, whatever, not voltmeter, what the brand of the meter thing for your wall plug, and it was like 50 watts, 100 watts maybe. And that includes the rack stuff too, I think. Yeah, Kilowatt, it's the brand name. But I do actually have more pedals than that. I didn't quite have enough room for it. And you can read through the Blue Sky thread about it. But it was funny, when I started building it, like, I knew conceptually I wanted pedals up off the ground. And I had bought this old desk table thing off Amazon that I saw that was really cheap. And I was like, oh, that would be a good way to do it. But it would only be like 20 pedals or something. And I started with that. And then I had an instrument rack for my keyboard thing. And I was thinking, oh, instead of a keyboard, what if I just had a sort of tray with a bunch of pedals on it? And so then I hunted around to find what was one that I could put the most things on it, because all the keyboard ones really only want to have 2 or 3 levels. And this has 4, I think. So yeah, so I didn't know what it would look like when I started, and in the end I had this. I was not thinking keyboard stands at all, but yeah, so I bought this thing that's basically a keyboard stand that has 4 levels, and then and then at the bottom it's got a rack unit that has one more tray on top of it, a bunch of pedals inside the rack unit at the bottom, and then the pedals over on the right on the top of the main rack unit. Do you have a few favorite pedals? I have let me this right here. Why is this not showing up? Oh, because I'm in Facecam only. Duh. Here we go. This pedal right here, this blue, like pale blue one, is a Boss chorus pedal that I bought in the 80s. I also bought a Boss distortion pedal in the 80s, but it got stolen. I have, so this is a JA set. I think this is the JHS Tube Screamer that has a bunch of different emulated Tube Screamer kind of models, variants. I do have an actual Ibanez Tube Screamer as well. I think I might have 2. Yeah, like I said, there are a bunch of pedals that aren't up here. This over here is a bunch of pairs of pedals. Amazon started selling these really cheap, and a couple other companies. They're made in China and rebranded. These really cheap pedals that are tiny. And so I bought several pairs of them, and it's a stereo signal where each side of the stereo goes through a parallel set of things. So they won't exactly match, because you won't turn the knobs to be exactly the same for them. Drawers has a bunch of pedals they're used together with some external switching to that drawer. That's what this is, except that they're these boards instead of drawers. But this down here is a switching system that switches on and off each of the boards, and then each of the boards has the ability to enable and disable all of the effects, so that you don't pay the cost of going serially through all of the effects. You go through this system, which only sends it out to 1 or 2 of them, to avoid noise overhead. Good old Boss white delay. Yeah, there's this is actually a row of delay pedals up here. Oh, right, that one. That's something else. But these are also delays and reverbs here. So yeah, this is a grab bag of things that I might use commonly or don't otherwise apply. This is all overdrives. This is all modulation effects, chorus and flangers and stuff. This is all delays, and this is all distortions. And these are all fuzzes, I think. These are all distortions and fuzzes, and these are all distortions and fuzzes, but I don't remember how they're split. And then this is all the stereo stuff. So basically, the guitar signal comes in here, goes through some of these boards, goes over to here, this thing, which routes them to some of these things, most of which are stereo. So this is a mono. These two are mono processing loop units that route out to these things. They have 12 slots, and 12 wasn't actually enough for this, because these 4 boards and this board are 5 of the 12 slots, but then pairs of these are wired up directly rather than the whole thing, and so I needed more than 7 pairs, and also these are wired here. So basically this can route to 24 things, but it's all mono. And then this one is a stereo one, so it can hook up to these in stereo. Then it connects to the audio interface, which is this thing right here. And it's actually plugged in direct. It's bypassing this right in this image. So yeah, I have the Steinberger spirits because they're light and so they feel comfortable. American Strat, a couple Ibanez's. I think the basses, I have a fretless bass. I can't remember what brands the bass and the fretless bass are. I have a 12-string, an electric 12-string. I have a acoustic, a Yamaha acoustic. I have a classical guitar, which is a nylon string acoustic. That's just some generic brand. An ex-girlfriend had it, and no, it's the Yamaha. I don't remember how I got the classical guitar. And a couple others. Go to Bandcamp. Yeah, this is old from before I started Rad, so this would have been 2007 or 2008. So the Ibanez nylon string, the steel string acoustic, 3 basses, and the mandolin, and the Rock Band guitars. Do I have a Voxel? Yeah, I do. Oh, whoops, I didn't mean to close it. One of these is a Voxel, I think. So one of these is a volume pedal and a wah. One of these is a volume pedal and one of these is a wah. And then the Digitech whammy. But it might be a Dunlop wah. I think I have a Vox wah and a Dunlop wah or something like that. I do have one of these round fuzz faces, but it doesn't fit on the board. Yeah, and I'm not a DIYer. I have a congenital shaky hand problem. It makes it hard for me to do certain things that involve fine motor stuff, but not like playing the guitar is fine. But soldering I can't do. The worst thing I can do is try to put, this is very old fashioned, but if vinyl record player in the old days they didn't have automatic switching, so you manually picked up the needle and you're picking up the head, an arm holding the head that holds the needle. But you pick up the needle and you put the needle down on the record. And trying to do that, my hand would go. So yeah, that's my recording setup. Oh, and you can see a couple other synthesizers here. There's the Morpheus and the Proteus, and then a bunch of effects units that I have from 10 or 20 years ago and don't use now. But it's Morpheus here, the Proteus here, and then these two, it's a Nano, which one is it, the Nano Piano or the Nano Bass? I think it's a Nano Bass. There was this I bought them, I wanted to buy them on eBay and I only found the one. There was this line of 3 products that Alesis made, the Nano Bass, the Nano Synth, and the Nano Piano, that are a third width, so you can put all 3 together on a rack. And I thought that would be fun to have. And I found the Nano Bass was, I think, the one I wanted the most. I think that's the Nano Bass. And the other 2 weren't turning up on eBay very often or were too expensive, so I didn't get them. This is a Roland I hunted around to find out what's the best Roland sample-based synth, because I bought those analog synthesizers I talked about. So I was like, let me get a modern sample-based synth that just can do everything, just to have one, because the one I had was not the old, because I had an old synth that was not very rich in, it was sample based, but it wasn't modern and didn't have lots. But I think I didn't actually buy a current thing. I think this was also an eBay purchase. It's like a JV something, JV 1080 or something like that. I Randy. Somebody asked about Randy Rhoads, which is like Ozzy Osbourne, I guess. Crazy Train, right? I've never been particularly like a metal person. My brother was more, so he owned a bunch of metal stuff in the 80s. So I've certainly heard it, but I'm not particularly familiar with Randy Rhoads playing. Yeah, well, the server rack is the same form factor. Like, the racks are racks, as far as I know. Music racks and server racks are the same rack specification. Obviously, the hardware tends to be deployed in different places, so they tend to, like, the bare metal for servers versus the fancier furniture for musical equipment. And this is that page that I went to, by the way. If you want, for some reason, to buy this old album I put out more than 10 years ago. I meant to put out a sequel. I was hoping to get a sequel done. When did this come out? In 2014. So yeah, I had a sequel that we were working on, and 2024, which was 10 years later, came and went, and we still hadn't finished it. So I don't know that we'll ever do it. The poster, there's two posters visible there. The Meat is Murder. It's probably the one you're seeing. But yeah, that link to that, like I said, that's from 2014. That predates this whole setup. I didn't have any of this gear. That was what that other screenshot, where it only had the 4 or 5 guitars. Well, it was 4 or 5 guitars plus basses, yeah. How many guitars do I have? I'm going to go count. I'll be right back. Looks like I have 12 guitars. 2 of them I haven't unpacked. 12 guitars plus a baritone guitar, which is basically a 6-string bass, but it's not quite bass length. It's shorter scale, but this particular baritone guitar is a little more in the bass direction than most baritone guitars. So it's a little longer than a regular guitar, and it is just tuned an octave below guitar tuning. But it did include the 12-string and it included 2 guitars I still haven't unpacked. Um, don't ask me why I have so many guitars. The baritone guitar uses custom strings for the baritone guitar, as I recall. I haven't changed them in a while. Since the bass is only going to have 4 strings. And like a 5-string bass goes 1 pitch lower, 1 string lower, whereas the baritone guitar has 2 strings that are higher than a normal bass guitar. And because the skill length is different, I think they're just dedicated strings for that guitar or for that class of baritone guitars, I think. But it's been a long time since I changed them. Oh, I know, I do have a 5-string bass. I bought that after I left Epic as well. So I have a regular 4-string bass, a fretless bass, the 5-string bass with active EQ, and maybe 1 more bass. So 3 or 4 basses. If we count the baritone guitar as a guitar, 3 or 4 basses, 13 guitars. 3 or 4 basses, 11 guitars, 11 electric guitars, 2 acoustic guitars. Why do I need 11 electric guitars? Well, okay, so here's the thing. I went through a period before I left Epic, when I was still making decent money. I was starting to do this thing where I was playing with having weird tunings, and I didn't want to have to keep retuning the guitar to different tunings. So I bought like 4 guitars, and the idea was I would just put each guitar on a different tuning. Which is, a huge indulgence, but at the time I was making money, so I could afford it. And then one of them is wired for a guitar synth. Maybe 2 of them are wired for guitar synth, actually. One of them is like the good Fender Strat that I don't play. One of them, this Ibanez clone that used to be the workhorse before the Spirits. So let's see. The 2 Spirits, the 2 Fender Strats and Strat-likes, 2 extra guitars for the open tuning stuff, or weird tuning stuff. That gets you to 6. The 12-string, that's to 7, and I said I have 11 electric guitars. The baritone, that makes 8. So there's 3 more that I don't know why. Oh, I bought a weird one that's sitar-like. It's supposed to be a little bit like an electric sitar. I haven't tried it yet. That's 9. So then there's like 2 unaccounted for, which is close enough. All right. I think that's it. We've just been talking about this thing, so I think we can wrap now. I mean, we've been rapping, but I think we can wrap. So basically, I have a music project that I started working on. I haven't touched it in a little while, but I put a lot of work into it, and I have about like 50 songs partway done. Some of them, a lot of incomplete lyrics, but the basic idea of them written. And it's unlike the thing that I linked to. The thing I linked to is sort of math rocky. It's very progressive and weird. And this project that I'm working on is more vibesy. It's sort of straight ahead, mellow 4/4 female vocalist music. And I bought the sitar. It's the Dan Electro Baby Sitar. I bought that as I was thinking that might be a nice flavor to try to work into that project. So when I get back to that project, that's when I'll unpack it and try and use it. But right now, I'm too caught up in Angine de Poitrine, the crazy math rock quarter tone stuff. Like that's just like so warped my brain. I can't even think about that other music, the vibesy 4/4 in a key, simple, super simple key thing. Like that band has pushed me so hard back towards progressive mentally, just in terms of like when I'm noodling at the guitar. I'm much more inspired by that stuff than the stuff that I had been trying to work on. So I'll get back to it. All right. Any more questions? Not music. Oh yeah. So off topic, but have you experimented with newer languages that push more advanced PLT ideas? We did talk a little about this in a previous stream. I have not experimented with any newer languages. I am very much the opposite. I mean, I'm not unwilling to try new things, but I tend to stick with the old things that I already know how they work and am skilled at, rather than having to relearn stuff. Any plans on when the next stream will be? Friday? I think I might do a Friday stream that's a regular stream, not a Voxel Friday stream, because I've did Monday and Wednesday did Voxel Friday streams. I think maybe on Friday I will try to do at the outdoor terrain rendering stream. Maybe. No promises. We're still in the no promises stage. For those of you who were there for the very first stream, what I said was I could imagine that what I might end up at would be streaming Monday, Wednesday, Friday. But I wasn't promising it. I wasn't even hoping it. I was just saying, well, if things went well, that's a potential outcome. And I have not streamed quite every Monday, Wednesday, Friday since then, but I have streamed many times approaching Monday, Wednesday, Friday. What was the planet Earth code with an actual sunrise you should before? Yeah, let's take a look at that. We can talk about that. What is, oh, that's that, yeah. So, yeah, this is, I was thinking about making a space game. So, the main thing about the space game, where did that thing that we were just looking at go? It's somewhere out here. There it is. So the main thing would be to have spaceships, and one of the things I would want to have would be very big space, capital ships. That's a classic thing in making space sims. And so I was looking for a method. I was looking for a method to texture a big ship, so it would have an okay amount of geometry, but maybe a very sophisticated texture. And so I made this system, which we talked about when I showed this off before, which is, it looks like it's hexagons, but it's actually a square textured tile mapped system. So there's a whole bunch of square tiles, and they've been arranged to make it look like they're hexagons by picking correct shapes in the tiles. And so this would let you paint a very complicated, varied texture across a flat surface of a capital ship that would show this level of variety, and I wouldn't have to spend the time on geometry for it. But anyway, so then while I was doing that, I was like, well, let's have a planet in the background, and rather than it just being a painted backdrop, like maybe you could see time advance, maybe you could, I don't know. So I was like, well, let's grab the NASA planet and let's draw that. And then I was like, well, let me figure out how to draw the atmospheric shading. And so the atmosphere then lets you, is accurate. Then I spent a lot of time on it. And so you can see that if you're at the correct angle, you get the sunset colors. And if you're too low, it turns pink. And if you're not at that angle, it's the more the colors you expect from the atmosphere. But maybe it would be, maybe if I made the spaceship game, you might have one mission where you're like in orbit at this altitude or something. But probably it doesn't need this level of detail at all. It was just, I basically put that effort. Once I started doing the atmosphere rendering, I was like, let me do it right, and spent a while on it. I'm right, have a write up of it. I just need to polish up the write up. But yeah, so it's really just intended to be a background to the space game. It's not really intended to be a good planet renderer. That was just me fooling around. So yeah, are the streams helping? Yes, absolutely. Like I've been streaming not quite every Monday, Wednesday, Friday, but nearly, and therefore been programming on those days. So not today, but I programmed last night, this morning, before the stream. And yeah, I don't think I would have been doing as much programming without the streams. All right. Any more? Would you reconsider making a video stream series about sparse virtual texting? I think I've said it all, haven't I? In the other one? I don't know. I don't know anything new. I haven't implemented it ever again since then, so I don't know that I have anything new to say. There is this tile map thing that I was just showing that's very similar to sparse virtual texting. It's just not sparse. But there's not much to it. You can actually see here in the code the setup for the atmospheric scattering. These are all constant, real world constants, basically, of how the scattering works in the in theory. And you can see it could be any planet, but I actually use actual units. That's a fun thing. In this space game, everything is actually coded in actual units using meters, despite the fact that the size of things are crazy big. Because as long as you're using floats, the precision problem doesn't matter if what you're looking at is far away. Like the precision problem that you run into is when you move far from the origin and there's stuff far from the origin with you. So in the space game, it would always, on every mission, the origin would be centered around where you start. And so anything far away can be at that actual distance, and the math just all cancels out and works correctly. It's kind of fun. Yeah, so the distance that the Earth is from the origin is the Earth radius plus the space station altitude is where the center of the Earth is drawn. There's no actual space station, but that conceptually, I think the starting point is at that altitude. Yeah, so if I... So this is an altitude an actual space station might be at. I think I was thinking maybe like a title screen when you're when you start up the game might be at a low, this kind of low altitude, looking at a space station as an attract mode screen kind of thing. Okay, haven't had any more questions, so we'll stop there. Thanks everybody for being here. We'll see you next time, which might be Friday, might not.